Last topic in this chapter is about logarithmic differentiation. And it's not too bad. I will explain you step by step. You can do it. I already made one video about the example, how to do logarithmic differentiation. And the whole review has many examples of logarithmic differentiation. The motivation here is, why do we do it? We have interesting types of functions when you have input raised to the input function. For example, how would you differentiate x to the x? What is x to the x? So think about it. If you have something looks like x to the 5, that's a polynomial. Derivative of x to the 5 is 5x to the 4. If you have something like 5 to the x, that's exponential function. Derivative of that function is 5 to the x natural log of the base 5. So what the heck x to the x is? Which one is that? A polynomial or exponential function? And the answer is both or neither. You cannot use any of those rules here. It doesn't work because we don't have a property that works for such a weird case, like x to the x, or like a function raised to a function, and both are variables. So to fix that or to get rid of the situation, we're gonna use log, because if we're gonna apply log to the both sides, this top p is gonna jump down and not gonna be a problem anymore, because log helped us to get rid of the exponents we don't like. Log takes the exponent, put it down, and you just multiply by that part, and now it's not complicated anymore. So that's why logarithmic differentiation is good. It basically makes your life easier. By the way, x to the x function is faster than exponential function, because exponential function is 5 to the x is growing, 5 to the x is growing really fast. Well, if x is growing to infinity and the exponent is growing to infinity, x to the x is growing really fast to infinity. So this function is actually super fast. Now, one more example when we want to use is when we don't want to work with quotient rule, product rule, and chain rule, when it's too many fractions. Something like this. This is the example I did before. We're not going to do it today. You can look my solutions here. You can differentiate this, but do you want to? Like, yeah, maybe you will always say no. But anyway, the whole point is, what if you have to? What if you're being paid to do that? What if it's your job? So you have to differentiate. Either you do it the way you see it's quotient rule and there's a product rule, each has chain rule, or you remember logarithmic differentiation. Logarithmic differentiation will tell you, hey, if you apply log to the both sides, then this fraction will disappear. Why? Because log of the division is log minus log. This product will disappear because log of the product is log plus log. These guys will go down and will not bother you anymore. And the answer will be, and the function will be much easier. It will be something like this. Nice log plus log minus log. And then you differentiate each. And that's actually very simple to differentiate logs. So that's where implicit differentiation works really well. And I told you before, many functions are too fast. When you differentiate those functions, they give you some speed. The speed might be too high. Computer might not be able to handle it as well. So you use logarithmic differentiation to slow it down, find the speed, and then use exponential function to reverse the process using inverse properties. So write down my steps. You don't have to follow them, but I think students like having steps, some kind of suggestions when you freak out during the exam. That's what I see. Like when you freak out, you don't know what to do. Step 1, take log of both sides. You can do it. Just write down with a pencil log of both sides. Then don't touch left-hand side for a while. For the right-hand side, you use laws of logs. Do you remember laws of logs? Basically, we showed you main 3 ones. Log of the product is log plus log. Log of the quotient, log minus log. Log of the exponential, exponent goes down. Or it can go up if you want. Third step, you differentiate both sides, and now implicit differentiation starts. Since left-hand side will be log, derivative of left-hand side will be 1 over y times y prime. You want to solve for y prime, and at the end there will be extra step. I will show you an example. You will see what's going to happen at the end. Basically, this is the rare case when y is given. Okay, let me keep it. You let me know if you're ready or not. In the first example, this lovely function y equals x to the x Let's find the speed of x to the x. That's pretty cool, actually, that this function even exists. How fast is x to the x? What is that? And now imagine it can be x to the x to the x to the x to the x anyway. Okay, let's do it step by step. I'll leave a little bit more for you to write. Step 1, it says use logs for both sides. I know students just lazy to write down, so they just take a pencil and do log here and then log here. I just don't want to have not pretty notes, so I'll rewrite it. It's going to be ln of y equals ln of x to the x. So just write down log of left-hand side, right-hand side. We can do it. Why not? We can do it. Applying log to both sides. Step 2, now it says the whole point you did it because you want to use log on the right-hand side to simplify the right-hand side. So keep the left-hand side the same until you start differentiating. And on the right-hand side, use properties of log. In this case, the whole point, I did not like this x. Super annoying to have this x over there. This is the reason why we don't know how to treat the function as exponential polynomial. So let's push this x down. It's going to be x times ln x. Now, instead of the complicated case, we have product. So what is x to the x? Think about that. X times x times x times x times x, x times. That's even hard to imagine how far it can go at infinity. But x times log, that's easy to imagine. X is a line, ln x is log, and then they just multiply. That's it. Step 3, when you finished using laws of logs, and you think it's good enough, now we start differentiating using implicit differentiation. That's why those topics go side by side. Implicit differentiation says treat y as dependent variable and x as independent variable. So derivative of log, did you do your homework? Do you remember? Derivative of log is 1 over x, or 1 over any input you have, right? So derivative of log of sine will be 1 over sine, and then times derivative of the function inside. Derivative of log of y is 1 over y, and then chain rule says times derivative of the function inside, which is y prime. Okay, you can write down dy over dx if you want, but did you see how I did it in my steps? I actually had a very nice notation. My nice notation looks like this: y prime over y. Ask me, did you get how I got y prime over y? 1 over y times derivative of y. So I can just put it up. It doesn't take tons of space anymore. Y prime. Right-hand side, product rule. Product rule tells me differentiate the first guy, which is 1. Copy the second one, which is log, plus copy the first one, which is x, times derivative of log is 1 over x. Since none of these were y's, no y prime pop out, right? So when you work with y, you differentiate something with y, y prime shows up. But none of those had y in it, so it was easy. Also, we assume x is not 0, so we can actually cancel out this x. How do you cancel? How do you cross x? Like this? So that's a very good joke. How do you cross the cross, right? Like, because x is a cross after all. So, but yeah, you know what I mean. I'm canceling those out and becomes 1. So this guy is 1. Then the whole version now looks like y prime over y equals ln x plus 1. The last step, almost the last step, but usually students combine these next two steps. I want to solve for y. Y prime equals. To solve for y, I just need to isolate y. What is on the way of isolation? 1 over y piece. So I'm going to multiply left-hand side and right-hand side by this y piece. Becomes y times natural log of x plus 1. Does that make sense? I just like to have y prime equals. That's the whole point. We're looking for y prime, so I want to have y prime equals. But then it was 1 over y, so I multiply by y. And it's always going to be the case. Left-hand side always going to have y equals, then ln of y, then 1 over y times y prime. So we're always going to have this step in orange. We always have to multiply the end by y. So implicit differentiation gives you the answer which includes x and y. I told you that before. This is the unusual part. Implicit differentiation works, but it gives you the answer which has both input and output. A little bit awkward, but we kind of just assumed it's fine. But with logarithmic differentiation, this guy is given. Let's go back at the beginning and check. It is given at the beginning. Logarithmic differentiation starts for the functions where you had explicit writing for y. Y equals something something. So the last step, let's plug this y back. 5th step is, so since y is given at the beginning, look at the very beginning, plug it in, plug y equals x to the x. And you get the answer. Y prime equals x to the x times natural log of x plus 1. That's one extra step. And usually students combine those two steps in one step because we know we need to multiply by y. Oh, that's not extra step over here. Step 3 and step 4. We had only 4 steps here, basically. Step 3 and step 4, usually students combine these two steps in one. Because you're multiplying by y, and you just go back, sneak really fast, what is x? What is y? X to the x. Then instead of multiplying by y, you're multiplying by x to the x. That's it. This is x to the x. Make sense? And that's the answer. So how fast is x to the x function? It is x to the x times log plus 1 fast. Very interesting. And when you use logarithmic differentiation, the same function will pop out all the time. Questions? What do you think? Is it different if you use implicit here? Well, we do. This step over here, when we differentiate over here, everything here is implicit. Implicit differentiation. If you want to differentiate right away, that's probably what you're asking. You want to differentiate from the beginning? How would you do it though? What is x to the x prime? We don't have any formula for that. Because we have formulas for different cases. We have formulas, let me write down. Let me write down at the end. I have a very nice note over here to answer your question. Why we could not just differentiate at the beginning? We know what? X to the 47 prime. X to the 47 is what? 47, x to the 46. Good job. That's a polynomial. We basically used power rule. Yeah, let me even write down. What rule did we use? We used power rule. Power rule. Second example. What if we had 47 to the x prime? Then what it is? That's exponential, right? Exponential tells you copy the exponential function first, copy, that's how we find derivative of exponentials, and then times derivative of the function the exponent, which is 1. But if you don't have e to the x, but it's 47 to the x, then don't forget to do natural log of the base, which is natural log of the 47. That's the formula how to differentiate exponential functions with different bases. The rule for this is called derivative of exponential function. So the question is, finally that's the whole point, 3. What is 47x raised to the 47x? And that exactly answers your question. How would you differentiate that? Because this basically is both or neither. How do we know when we use power rule? The input is in the base, then you know it's polynomial, you use a power rule. How do we know when to use exponential function? The input is an exponent, then you know we use exponential functions differentiation. But what if input is both at the base and the exponent? Is this a power rule or exponential differentiation? Both or neither? Mathematics says we don't give you a formula for that. Use logarithmic differentiation. That's what we say. So it's not enough formulas to hold. So we created a whole methods that will help in situations like that. So the answer to your question, there is no way to differentiate x to the x unless you use logarithmic differentiation and transform x to the x into normal product x times log x. Makes sense? So for this one, what should I write down? What should I use for this one? What's the answer? Use logarithmic differentiation. Why? Because BC, it's because B/C. Because we have the case input raised to the input. That's why. Power rule is input to the number. Exponential is number to the input. Input to the input is an unusual case, which is solved using logarithmic differentiation. That's what we teach you, and now you know. It's like kind of a secret weapon, and we just showed you how to deal with it. Very interesting. Not only is for those cases, but if you see something like x to the tangent x, and in the exam I was reviewing, there's cases like that. 4x to the tangent x, that's the case. That's the one you need to use logarithmic differentiation. But also this case, we're not going to do this problem. There's so many of them. But cases like this, and I already explained why. Tons of products and quotients, and they ask you to differentiate. And what if I don't say that to use logarithmic differentiation? What if we need you to decide? Then you can do it. You can do product rule, quotient rule, chain rule 5 times here, whatever. But do you want? With logarithmic differentiation, it's faster. It's only 4 steps here with logarithmic differentiation, and you get the answer very fast. But you need to know all the rules of logs to do that fast. Questions? What do you think? Did you practice derivatives of logs and x at home? I think that chapter is not too bad. Did you like it? That one is not too bad. Usually people don't argue that one was pretty pleasant. And after this, we're going to go to trigonometric functions. So you might actually miss logarithms and not logarithms. One last example to ask, to check did you do your homework or not. Do you know what is 6e to the x cosine x prime? Can you differentiate that? Just a last example of this chapter, exponentials and logarithms. Last example. Can you differentiate that? Just to point out, last time, how to do it, especially if you missed classes, but your homework was supposed to be a good practice. You see exponential, how do I know what to do? I see no input at the base. 6 and e are numbers. Since there is a number raised to the input, then I use exponential function properties. To differentiate the exponential function, I know exponential function tells me copy first. Copy first. 6e to the x times cosine x. So that's the good part of differentiating exponential functions. You just copy it. Log says divide by everything inside. Exponential copy, and then it says times, and then chain rule. Chain rule goes in. And chain rule says look at the exponent. And that's the unusual part of it, because exponent is somewhere upstairs, and you have to differentiate that piece. But that's what chain rule tells you. Now you can look inside, but just inside part is elevated to the exponential level, exponent level. Derivative of that product should be used to product rule, which is 1 times cosine x plus, let's do minus x sine x. Here's a very standard example for the exam. Can you do this fast? This is product rule. If you can't, you have couple weeks to prepare yourself, and then we're going to test you a lot. And usually we test on many exams. Don't think it's going to be one exam testing this. This is going to be in calculus 2, calculus 3 class, differential equation class. The earlier you do it faster, the better for you. And you just feel very satisfied that you can do it fast and you know what's going on and you can catch all the mistakes.